a copper-clad board. Punch component mounting holes. Paint the pattern using etch-resist ink pen, Indian ink or enamel paint. Etch a painted copper-clad board. Trace the component side pattern and make the components. Drill holes on the PCB. Revert tags or terminals at input and output points. Introduction about printed circuit board. A printed circuit board, shortly called as PCB, is an electronic assembly that uses copper conductors to create electrical connections between components. Printed circuit boards provide mechanical support for electronic components so that a device can be mounted in an enclosure. A printed circuit board, PCB, is a sheet of insulating material such as fiberglass with a metallic circuit or track printed or etched on it for electrical conductivity. A PCB is found in almost all electronic products that we use in our daily lives. Mobile phones, TVs, computers, military weapons, aeroplanes, satellites, etc. Advantages of using PCB boards: compact in size, easy to repair, reduces electronic noises, low cost, increased reliability. Tools required: center punch sharp tip, wooden mallet, hand drill or push type drill gun, bench-wise or table-wise, glass rod 30 cm long, carbon paper A4 size, etch resist ink pen black or Indian, copper clad 1 ounce 75 x 60 mm phenolic single side, ferric chloride in liquid or powder form 50 ml, thinner 100 ml, turret type termination tags, reverting type, plastic tray 30 cm into 15 cm approximately, painting brush. Components of a printed circuit board. Let us discuss the parts on the PCB boards. Substrate. A PCB substrate is the material that holds the traces and components that make up the foundation of a printed circuit board. Copper layer. The copper layer is a thin layer of copper foil that is laminated to the board by heating. When we speak of different layered PCBs, we are referring to how many copper layers they consist of. If you are creating a single-sided PCB, the circuit board has one layer of conducting material on one side, and the other side is used for incorporating different electronic components. Solder mask. Due to the solder mask, the PCB is often green, though it can be other colors as well, by keeping the copper lines from coming into contact with metal or solder. This layer aids in giving insulation to them. Silk screen. A white color silk screen layer is applied to the upper part of the solder mask, where different letters, symbolic representations, and numbers are written that are used to connect the components. Trace. It is a highly conductive track that is used to connect the various components on a printed circuit board, including the IC, capacitors, and resistors. Pad. A pad is the exposed region of metal on a circuit board that the component lead is soldered to. Preparing the tracks on copper-clad board. Clean the copper side of the 75 mm into 60 mm single-side copper-clad board using soap and water. Dry it using a piece of cloth. Presence of oil or dust on the clad hinders transferring of the layout on the board. Take a fresh carbon paper of 85 x 70 mm and fix it on the copper-clad board. Take out the PCB circuit pattern diagram of power supply prepared for making power supply. Fix the circuit pattern over the carbon paper. Use adhesive tapes at several places such that the layout drawing sheet does not slip off while tracing. Make punch marks using a center punch, as the centers of all inner circles and the mounting hole circles. Trace all the pads and connecting tracks using 2HP pencil. Take out both the circuit pattern diagram sheet and the carbon paper fixed on the clad. Check if the all traced impression of the pattern of the copper clad is clearly visible. Use etch-resisting pen or a fine painting brush and Indian ink or enamel paint, ink the pattern. If the ink flows slightly beyond the traced pattern circles and lines, do not try to correct it. Allow the ink to dry for 5 to 10 minutes. Correct the excessive paint flows outside the intended pattern by using a sharp-tipped knife or half-shaped blade. Allow the pattern to dry up in sunlight for at least 3 to 4 hours. The drying period depends on the paint or ink used. Etching the painted laminated board and drilling holes on PCB. Take about half liter of lukewarm water in a plastic tray of approximately 30 cm into 15 cm. Put on hand gloves. Add 3 spoonfuls of ferric chloride etchant to water and stir the solution using a glass rod. Ferric chloride solution is injurious to bare skin. Slide the painted copper cladboard PCB1 into ferric chloride and water solution with the copper clad side facing upward and visible. Move the tray up and down, left and right, such that the solution is agitated adequately in increasing the etching process. Repeat the process for 10 to 15 minutes and observe the unpainted portion of the copper clad getting etched off. Take out the board from the ferric chloride solution and check visibly if the unpainted copper is completely etched. If not, put the board back into the solution and allow the board to remain in the solution for 5 to 10 minutes. Take out the board from the ferric chloride solution and wash the board thoroughly in running water. Apply a small quantity of detergent powder and wash it again in running water. Allow the board to dry in open air or by placing it in front of a fan. Using a thick brush, apply thinner or alcohol or petrol on the painted side of the board and remove the ink using a dry cloth. Repeat the process until the paint is completely removed and the copper pattern is clearly visible. Wash the painted circuit board with water and dry it using a piece of cloth. Fix the board with a wooden block on a vise. Using a hand drill or push drill gun fitted with a dia 0.8 mm drill bit. Drill holes at the corner mounting points by using a drill bit of dia 2 mm. Clean the drilled board from burn and other dirt using a cloth or a brush. Tracing and marking component layout on PCB. Cut the component layout diagram for PCB at its marked borderline. Fix a carbon paper on the non-pattern side of PCB1 with the carbon facing the board. Take the component side layout diagram of PCB1 and fix the component layout pattern on the non-pattern side of the PCB. Check alignment of holes using a ball pen or poker. Trace the pad points and component by using a 2HP pencil. Remove both papers from the board. If necessary, touch up the tracing using 2HP pencil. Retrace the component symbols by using a thin tip permanent marker pen and valves on the component side of PCB. Allow it to dry for a few minutes. Revert 2 number of 2 mm post type terminal tags at the AC input, 2 numbers at battery input terminals and 4 number of turret type terminal tags at the output points marked on the PCB. Solder the reverted tags on the solder side of the PCB to ensure good electrical joint. Recap. After watching this video, you can make a printed circuit board for a power supply circuit. Thank you for watching. Have a nice day.
Hello everyone. Today let's discuss how to construct a simple circuit containing UJT for triggering and FET as an amplifier. Session objectives. At the end of this video, you will be able to construct UJT relaxation oscillator for triggering and test. Identify the terminals with specification of JFET and test an N-channel JFET. Construct an AC voltage amplifier using JFET and find the gain. Plot the graph of gain of the amplifier at different frequencies. Let us collect the instruments and components to do these practical. Dual channel oscilloscope 20 MHz 1. Power supply unit 0 to 30 volts 2 ampere variable 1. Function generator 2 to 200 Hz 1. General purpose PCB 4 by 8 cm 1. UJT 2N2 1. Resistors 47 ohm 1 by 4 watt 1. 470 ohm 1 by 4 watt 1. 2.2 kilo ohm 1 by 4 watt 1. 1 mega ohm 1 by 4 watt 1. 45 kilo ohm 1 by 4 watt 1. 10 kilo ohm 1 by 4 watt 1. Potentiometer half watt 470 kilo ohm 1. Capacitors. Capacitor 0.02 microfarad 25 volt 1. Capacitor 5.6 nanofarad disc type 1. Capacitor 270 nanofarad 1. Capacitor 6.8 microfarad 24 volt electrolyte 1. JFET BF245B BFW10. Sleeves red, green, yellow, black 4. Task 1. Construct UJT relaxation oscillator for triggering and test it. Identify the terminals of UJT from the datasheet. Test the UJT using digital multimeter. Measure the resistance between B1 and B2 terminals. Set your digital multimeter in resistance mode. Connect the positive lead of the multimeter to the B1 terminal and negative lead to the B2 terminal. The multimeter will show a high resistance around 4 to 10K. Now connect the positive lead to the B2 terminal and the negative lead to the B1 terminal. Again, the multimeter will show a high resistance around 4 to 10K. Also, both readings will be almost the same. Reverse bias the emitter junction. Set your digital multimeter in resistance mode. Connect the positive lead of the multimeter to the B1 terminal and the negative lead to the emitter. The multimeter will show a high resistance around 4 to 10K. Now, connect the positive lead to the B2 terminal and the negative lead to the emitter. Again, the multimeter will show a high resistance around 4 to 10K. Also, both readings will be almost the same. Forward bias the emitter junction. Set your digital multimeter in resistance mode. Connect the positive lead of the multimeter to the emitter and the negative lead to the B1 terminal. The multimeter will show a low resistance around 100 ohm. Now, connect the positive lead to the emitter and the negative lead to the B2 terminal. The multimeter will show a low resistance around 100 ohm. Also, both readings will almost be the same. The test is almost like forward biasing a diode. Assemble the relaxation oscillator on the general purpose PCB by referring the circuit diagram. Get the wired oscillator across the resistors R4. Energize the circuit with the stipulated DC. Check the triggering pulses by using CRO between emitter and base and sketch these waveforms in tabulation. Frequency is equal to 1 by T, where T is the time period in seconds. Time period condition 1. T is equal to when C is equal to 0.02 microfarad. And R2 is at one extreme end. R2 is equal to 0. Time seconds is equal to R1 plus R2 into C, where R1 and R2 are in ohms, C in farad. R1 is equal to 2K2 ohms and R2 is equal to 470K ohms variable. Value of R2 at middle is equal to 235K ohms. R2 at the other end is equal to 470K ohms. Task 2. Identify the leads of given JFETs and find specifications of JFET using data manual and testing of N-channel JFET. Take a JFET and record the type number of the JFET and enter it against its label number in tabulation, referring to data manual. Identify and record the following important specifications of the JFET based on its type number: polarity of the device, N-type or P-type, maximum drain source voltage, VDS, maximum gate source voltage, VGS, maximum drain current, ID, maximum forward gate current, IG, pinch off voltage at ID equal to 0, VP, maximum power dissipation, Pmax, package type, pin diagram. Identify the leads of the JFET from the identified package type and put sleeves of suitable length to the leads following the color scheme given: drain, red; source, green; gate, yellow; shield, black. Terminals of the ohm meter, multimeter, and insert the red probe to the meter terminal connected to positive of internal battery and black probe to negative of the internal battery by referring chart 1. Set the meter to R into 1000 range. Refer given table and test the given JFET. Task 3. Construct and test an AC FET amplifier and plot the graph. Construct an AC voltage amplifier using N-channel FET as shown in the circuit diagram. Construct the circuit on a breadboard or on a general purpose PCB. If you're wiring the circuit on a general purpose PCB, use base for the FET to ensure that it does not get damaged. Power on wired circuit. Feed input at 10 kHz and level from 1 mV to 1 volt in steps of 100 mV. Measure the corresponding output levels by using CRO and record in tabulation. Calculate the gain of the amplifier with an input of 400 mV at frequencies 40 kHz, 80 kHz, 100 kHz, 120 kHz and at 150 kHz in tabulation. Plot the graph for frequency versus gain. Thank you so much everyone for watching this video. I hope you have learned the objectives, how to construct a simple circuit containing UJT for triggering and FET as an amplifier. Please do practice this with your instructors. Happy learning!
Hi everyone. In this video, let us discuss how to troubleshoot simple power supplies. Objectives. At the end of this video, you will be able to carry out step-by-step troubleshooting of a power supply with a bridge rectifier and capacitor filter. Carry out a shortcut method of troubleshooting the power supply through the problem tree and service flow. Bridge rectifier circuit. Let us briefly discuss the bridge rectifier circuit that we are going to use for troubleshooting. A bridge rectifier is a circuit that is usually used to convert alternating current AC to direct current DC. Most of the electronic components work under DC supply. So, to convert the AC main supply to DC supply, these bridge rectifier circuits are used. Bridge rectifiers are widely used in power supplies that provide the necessary DC voltage for electronic components or devices. Bridge rectifier circuit consists of step-down transformer, 4 diodes, capacitor as filter circuit as shown in the circuit diagram. Tools required: trainee kit 1 number, soldering iron 25 watt 250 volt 1 number, solder, soldering flux, digital multimeter. Materials required: bridge rectifier power supply circuit with filter, spare components as required. Task 1. Troubleshoot defects in bridge rectifier power supply. Step 1. In the given power supply, check for any one of the physical defects listed below. Record the observed defects in Table 1. Service the defects. 1. Loose or open wire connections. 2. Loose, open component led connections. Dry solder points. Shorting of terminals due to solder spray or bad skinning or blending of wire ends or component leads. Serial number 1. Name of the defective component, diode. Nature of defect observed, lead broken. Equivalent, if any of the components to be replaced. Null. Specification of the components to be placed. Diode 1N4007. Serial number 2. Name of the defective component, transformer. Nature of defect observed, secondary winding open circuit. Equivalent, if any, for the components to be replaced. Null. Specification of the components to be placed, transformer 240 volt, 12 volt, 500 milliampere. Serial number 3. Name of the defective component, capacitor. Nature of defect observed. While checking with multimeter, resistance value remains unchanged. Equivalent, if any, for the components to be replaced. Null. Specification of the components to be placed. Electrolytic capacitor. Serial number 4. Name of the defective component, soldering point. Nature of defect observed, dry solder. Equivalent, if any, for the components to be replaced. Null. Specification of the components to be placed, desoldered. Step 2. Trace the circuit wiring and check the correctness of the following. Polarity of diodes, polarity of polarized capacitors. Correct the polarities if found defective and record the defect observed and polarity corrected in Table 2. Table 2. Serial number 1. Name of the components, diode D1. Polarity checked, yes. Serial number 2. Name of the components, diode D2. Polarity checked, yes. Serial number 3. Name of the components, diode D3. Polarity checked, yes. Serial number 4. Name of the components, diode D4. Polarity checked, yes. Serial number 5. Name of the components, capacitor C. Polarity checked, yes. Step 3. Open one of the wire ends of the power cord connected to the power supply. This will disconnect the transformer primarily from power cord. Step 4. Using a continuity tester, check the power cord for any one of the following defects and record the defect observed if any. 1. Open or shorted wires in the plug. Open or shorted wires in the 2-core cable. Step 5. Check the continuity of transformer primary winding. If found open or short the coil, record defect. Step 6. Remove the wires soldered at the secondary winding terminals of the transformer. Check the continuity of the secondary winding. Record your observation. Step 7. Open one lead of each diode. Check the condition of the diodes. Step 8. Open one of the leads of the capacitor. Check the condition of the filter capacitor by carrying out the capacitor action test using digital multimeter. 1. Take a multimeter and set it in resistance mode 1 kilo-ohm. 2. Place the multimeter probes across the capacitor that has to be tested for correct polarity, positive to positive and negative to negative. 3. Multimeter will show some readings and keep increasing the resistance value, eventually reaching infinity. It means the capacitor is in good condition. 4. If the multimeter readings do not change or don't show any readings, then the capacitor is not good and has to be replaced. Step 9. Check the condition of the bleeder or load resistor. Record your observations. Step 10. Collect and test the new components to replace the identified defective components. Step 11. Replace the defective components with the new components and solder back all connections opened while testing. Step 12. Connect serviced power supply to AC mains and switch on main supply. Check and record the output condition under the heading Final Condition after servicing. Step 13. Final condition of power supply after servicing. Check for A. Output voltage level, B. Ripple voltage VR, PP in output DC. Task 2. Troubleshoot defects in power supply using shortcut or logical approach method. Step 1. Switch on the given defective power supply unit and record the identified defect in record sheet. Step 2. Refer the problem tree corresponding to identified defect. Step 3. Refer the service flow sequence SFS1 or SFS2 depending on the identified defect of power supply. Follow the logical sequence to service the defective power supply. Step 4. Record the identified component defects and remedial actions. Measure taken in Table 2 of the record sheet. Refer the problem tree corresponding to the SFS for finding the possible causes of the defects. Whenever any component is replaced, record the specification of the replaced component in Table 2 of the record sheet. Once the servicing as per SFS is complete, record the final condition of the power supply in Table 2 as done. Step 5. A. Output voltage level. B. Ripple voltage VR peak to peak in output DC. Step 6. Refer service flow chart 1 and 2 and follow the sequence of approach. Step 7. Interpret the problem tree chart 1 and 2, PTC1 and PTC2 and locate the exact fault or repair. Service flow sequence SFS1. Nature of defect, low output DC. Recap. After watching this video, you can troubleshoot the simple power supply. Hope this video was useful to you. Have a great day. Thank you. Hi everyone. In today's video, we discuss how to construct power control circuits using power electronics devices like SCR, DIAC, TRIAC, and IGBT. Objectives. At the end of this video, you can able to assemble and test a lamp dimmer cum fan speed regulator using TRIAC and DIAC. Construct and test a power control circuit using SCR. Construct and test a power control circuit using IGBT. Tools required. Let us collect the tools, equipments, and materials required to do these practicals. Soldering iron, 25 watt, 250 volt. Lamp load, 60 watt, 250 volt. Table fan, 80 watt, 240 volt. Universal motor. Hand drilling machine with bit, dia 8 mm. Triggering pulse module for pulse generate. Resistors. 1. Range 180 ohms, 1 watt plus or minus 5%. Quantity 1 number. 2. 4K7 12 watt 5%. 1 number. 3. 470 kilo ohms 1 by 4 watt 5%. 1 number. 4. 10K 2 watt 1 number. 5. 470 ohm 1 number. 6. 1 kilo ohm 2 numbers. Potentiometer linear 250K 16 mm plastic shaft. Capacitors. 1. Range 0.1 microfarads 415 volts. Quantity 4 numbers. 2. 2.2 K picofarad 1 number. 3. 100 picofarad 1 number. Solder. Solder flux. General purpose PCB. Inductor 25 SWG 40 turns on 10 mm ferrite rod with former made of lateroid paper. Pot meters 1 kilo ohm 1 watt. Diode 1N4007. Transistor BD135 BD136. SCR C106D or equivalent. Diac D3202. Triac BT136. IGBT HGTG 12N60. Brief introduction to diac and triac. Let us briefly on diac and triac. Diac or diode for alternating current is a two-terminal semiconductor device that can conduct current in either direction depending on the voltage connected to its terminals. When the voltage between the two terminals is greater than the breakdown voltage, the diac conducts and the current goes in the direction from the higher voltage point to the lower voltage point. You could see the symbol of the diac, which shows that it conducts in either direction only after the breakdown voltage. Diac is mainly used to trigger various power semiconductor devices like triac and SCR. It is also used as an AC switch as it can conduct in both directions. Triac is also known as a triode for alternating current. Triac is a three-terminal semiconductor device that conducts current in either direction which triggered. The symbol of the triac shows that it can allow current in either direction with gate control. There are two main terminals, namely MT1 and MT2, and the remaining terminal is gate terminal. Some of the major applications of triac are dimmer switches for lamps, output controllers for electric heaters, speed controllers for motors. Constructing power control circuit using triac and diac. Clean the printed circuit board PCB. Check the circuit components and confirm their working condition. Assemble the control circuit referring to the circuit schematic diagram. Keep the PCB on any insulated material. Keep the potentiometer in mid position. Put AC main single pole single through SPST switch mounted on the gang box off. Connect a test lamp at the mains output socket mounted on the gang box. Vary POT position such that the light intensity of the output lamp gradually decreases and becomes minimum or zero. Record the status of the lamp intensity at one extreme position of the pivot. Increase the intensity of lamp gradually by turning the pivot from minimum position to maximum position. Check and record the light intensity at other extreme position of the pot. Remove the lamp load connected at the controller output of the lamp dimmer circuit. Connect a table fan to the controlled AC output of the wired circuit. Switch on the AC mains supply to the circuit. Vary the POT from one end to the other. Observe and record the speed of the fan at minimum, middle and maximum position of the POT. Briefly discuss SCR. SCR is a semiconductor device that acts as a rectifier like a diode, except the diode is uncontrollable, but the SCR can be controlled using the gate terminal, hence it is called a controlled rectifier. A silicon-controlled rectifier is a three-terminal, anode, cathode and gate, 4-layer PNPN and 3-junction J1, J2 and J3. SCRs are mainly used in AC power control applications such as lamp dimming, power regulation and motor control. Constructing power control circuit using silicon controlled rectifier. Construct power control circuit using silicon controlled rectifier. Prepare a PCB for the given dimensions. Check the sizes of the components with the soldering position on the PCB. Check the PCB tracks and clean PCB. Test the components to confirm its working condition. Using suitable wires, make connections for the POT, switch, 6A flush type socket, 3-core cable mains, 3-pin top with the wired circuit on PCB. The wire connections made is to test the wired power control circuit. Test the working of the wired circuit by connecting a test lamp load at the output of the speed control circuit. Find the lamp glow bringing the two extreme positions of the speed. Test the speed controller using table fan as load and record your observation. Introduction to IGBT. Let us briefly discuss on IGBT. IGBT stands for Insulated Gate Bipolar Transistor. An insulated gate bipolar transistor is a three-terminal power semiconductor device primarily forming an electronic switch. It was developed to combine high efficiency with fast switching. It consists of 4 alternating layers that are controlled by metal oxide semiconductor gate structure. Applications of IGBT. 1. AC motor drives, that is inverters. 2. DC to DC power supplies, that is choppers. 3. UPS systems. Construct power control circuit using insulated gate bipolar transistor IGBT. Wire the circuit as per the circuit diagram and connect the cables for connection. Set the input AC single phase supply to 120 volt and connect to the supply points E1 and E2 through a variac. Switch on the triggering pulse generator and set the pulse control minimum position. Switch on the variac. Increase the triggering pulse control to rotate AC or DC motor. Universal motor rotates slowly with abnormal sound. Switch off both the control circuit and triggering pulse circuit. Set the variac voltage 240 volt and switch on the triggering pulse. Reduce the speed by controlling triggering control knob if motor rotates with high speed. Switch off both the circuits. Universal motor should not be allowed to run without load. Ensure the motor RPM varies as per the variation of trigger pulse control. Recap. I hope after watching this video, you can construct a power control circuit by using power semiconductor devices like SCR, diac, triac and IGBT. Thank you for your time. Have a wonderful day. Hi everyone. In this video, we are going to discuss how to construct a variable DC stabilized power supply using an IC. Objectives. Test the components. Construct and test a variable IC regulated power supply. Test the voltage regulation at various load. Brief introduction to DC stabilized power supply. A variable DC supply is an integral part of any power supply unit used in electronic equipment. Generally, it converts line frequency AC to DC. A line frequency bridge rectifier circuit is used. Usually, the output of the rectifier is pulsating DC or DC with AC content. To get pure DC as an output, a filter circuit is used. The filter circuit uses capacitors to remove the AC content from the DC. But these pure DC voltages are not constant and fluctuate. Most of the electronic components require a constant DC output voltage. So, the fluctuating DC is given to ICLM317 and a constant DC or stabilized DC voltage is taken as output. The LM317 device is an adjustable 3-terminal positive voltage regulator capable of supplying more than 1.5 ampere over an output voltage range of 1.25 volt to 37 volt. Variable DC power supplies can be used in many applications, like applying variable voltage to DC motors, battery charging circuits, and DC to DC converters. Tools required: soldering iron 25 watt or 250 volt, digital multimeter, general purpose PCB, step-down transformer 220 volt, 24 volt, 500 milliampere, diodes 1N4002, capacitors as required, LED red, resistors as required, 3-terminal voltage regulator LM317T TO 220 package, 1 ampere slow blow fuse with fuse holder, hook-up wires as required, heatsink for TO 220 package, rheostat 100 ohm 1 ampere, testing the components. Identify the terminals of the diode, silver coated as the cathode and the other side as the anode. Switch on the digital multimeter and set it on diode mode. Place the multimeter probes on the diode terminals, like the positive probe on the anode and the negative probe on the cathode terminals. This means the diode is forward biased. The displayed voltage value should be between 0.6 and 0.7 to indicate a healthy and ideal diode. Reverse the meter's terminals now by connecting the black probe to the anode and the red probe to the cathode. This is the diode's reverse biased state in which no current passes through it. As a result, if the diode is functioning properly, the meter should show OL or 1, which is comparable to an open circuit. The diode is faulty if the meter displays readings that are unrelated to the previous two circumstances. These are two types of diode defects, open and short. Testing of capacitors. Take a multimeter and set it in resistance mode at 2 kilo ohm. Place the multimeter probes across the capacitor that has to be tested for correct polarity. Multimeter will show some readings and keep increasing resistance value, eventually reaching infinity. It means the capacitor is in good condition. If the multimeter readings do not change or don't show any readings, then the capacitor is not good and has to be replaced. Testing of transformers. Continuity test. Set the digital multimeter in continuity mode. Place the probes between the primary terminals and check for a beep sound, same as on the secondary side. If no beep sound is produced, then the transformer winding is open or damaged. You can also check the transformer by measuring the resistance of the windings. Set the multimeter in resistance mode and measure the resistance of the primary and secondary sides. The resistance of the primary side must be greater than that of secondary side. In the case of a step-up transformer, the resistance of the primary side should be less than that of the secondary side. Before connecting the transformer to the circuit, you can test the transformer by giving the AC supply to the primary and check the desired voltage on the secondary side. Testing of IC LM317T. Before connecting the IC LM317T to the circuit, test the IC separately by connecting the DC input to the correct pins shown in the circuit diagram. using the variable resistor to check for the desired output. Procedure. Check the given general purpose PCB for the following defects and correct them to take a new board. Broken tracks, joined tracks, closed holes. Clean the copper side of the PCB using alcohol or other cleaning agents. Wash, wipe and dry the PCB. Construct a variable regulated output power supply on the given general purpose PCB. Referring to the circuit schematic diagram, all components except the transformer to be mounted on PCB use suitable heat sink with IC317T. Note: solder all components except the fuse and transformer on the given PCB. A single-phase AC supply of 50 Hz at 240 volts is converted to 24 volts AC using the step-down transformer, and 24 volts AC is given to the bridge rectifier to convert into DC. The pulsating DC is then given to the capacitor filter circuit and pure DC is given as input to the ICLM317 and finally output as a variable stabilized DC power supply. Connect the secondary of 240:24 volt transformer to the wired circuit. Switch on mains supply. Switch off mains supply immediately if burning, smoking, overheating and sparks are observed in any of the components and report to your instructor. Check the IC and ensure that it is not heated up. Measure and record the unregulated DC input and the maximum variable voltage of the regulator under no load condition. Set the output to plus 15 volts and load the output using a loading rheostat in steps of 200 mA up to 600 mA. In each step, measure and record the output voltage and the ripple voltage. Load current is restricted to 600 mA as heat sink is provided to the IC may not be the ideal one. Calculate and record the output regulation and ripple rejection of the regulator. Ripple rejection ratio is a measure of how well a circuit rejects ripple coming from the input power supply at various frequencies. Short the load terminals momentarily by using DC current meter 0 to 1 ampere range and record the short circuit fault back protection current level. Recap. I hope after watching this video, you can construct a variable DC stabilized power supply using IC. Hope now you know to test the components, construct and test a variable IC regulated power supply. Test the voltage regulation at various load and ripple rejection. Thanks for watching. Have a nice day. Hi everyone. In today's video, we are going to practice various logic using logic gates and circuits. Objectives. At the end of this video, you shall be able to construct an OR gate using switches and verify its truth table. Construct an OR gate using IC7432 and verify its truth table. Construct AND gate using lamps and switches. Construct an AND gate using IC7408. Construct a NOT gate and verify the truth table using a transistor. Introduction to logic gates. Let us discuss about the logic gates. An essential idea in digital electronics is logic gates. To perform logical operations on one or more binary inputs and produce a single binary output, logic gates are utilized. Logic gates are used in microprocessors, microcontrollers, embedded system applications, computers, and electronic circuits. There are different types of logic gates available. Here we are going to discuss the basic gates, namely the OR gate, the AND gate, and the NOT gate. Serial number 1. Logic gates OR gate. IC number IC7432. Symbol. Truth table. Inputs A0, B0, output Y0. Inputs A1, B0, output Y1. Inputs A0, B1, output Y1. Inputs A1, B1, output Y1. Serial number 2. AND gate IC7408. Symbol. Truth table. Inputs A0, B0, output Y0. Inputs A1, B0, output Y0. Inputs A0, B1, output Y0. Inputs A1, B1, output Y1. Serial number 3. NOT gate IC7404. Symbol. Input A0, output Y1. Input A1, output Y0. Typically, standard logic gates are available on 14-pin DIL chips, dual inline. The number of gates per IC varies depending on the number of inputs per gate. Usually, all logic gates IC works with 5-volt DC supply. IC7432 OR gate IC 7432, which consists of 4 logics as shown in the diagram, consists of 2 inputs and 1 outputs, pin 1 and 2 as input and pin 3 as output, or pin 4 and 5 as input and pin 6 as output. Usually in all logic gate ICs, the 14th pin is used for power supply and the 7th pin for ground. IC7408 AND gate IC 7408, which consists of 4 logics as shown in the diagram, consists of 2 inputs and single output, pin 1 and 2 as input and pin 3 as output, or pin 4 and 5 as input and pin 6 as output. Usually in all logic gate ICs, the 14th pin is used for power supply and the 7th pin for ground. IC7404 NOT gate IC, which can be identified by the number IC7404, which consists of 6 logics as shown in the diagram, consists of single inputs and single output, pin 1 as input and pin 2 as output, or pin 3 as input and pin 4 as output. Usually in all logic gate ICs, the 14th pin is used for power supply and the 7th pin for ground. Tools required: trainees kit 1 number, voltmeter 1 number, data manual 1 number, digital IC tester 1 number. Components required: single pole switch any type by toggled switch 240 volt 6 ampere 2 number, lamp 250 volt 100 watts 1 number, LED red 5 mm 2 number, ICs 7408 quad and gate 1 number, IC 7432 quad or gate 1 number. Connecting wires as required: solder flux as required, DC power supply 5 volt 1 number, SPDT switches 2 number, general purpose IC test board or pin board 1, transistor BC147 1 number, resistors carbon film as required, LED 5 mm green 2 number, IC 7404 hex inverter 1 number, hookup wire as required. Construction of OR gate: wire an OR gate circuit on a test board pin board as shown in the circuit diagram. Apply logic level inputs to A and B of the circuit as given in table. Record the output lamp condition in each case and verify its truth table. 0 indicates switch is off. 1 indicates switch is on. Constructing a quad 2-input OR gate using IC 7432. Insert the IC 7432 into the IC base of the general purpose IC test board. Connect the 2 toggle switches S1 and S2 at pin numbers 1 and 2 respectively and output through the LED from pin number 3. Connect pins 7 and 14 to ground and supply respectively. Set the switches S1 and S2 to apply input logic levels as shown in logic table, record the output logic level and verify its truth table. Do the same connections to verify the other logic circuits with the corresponding input and output pins as in the circuit diagram and note them down in the tabulation. Constructing AND gate using two switches with lamp and verify its truth table. Construct AND gate using two switches with lamp and verify its truth table. Apply different logic levels to the inputs A and B as given in the truth table. Also, you could observe that if both switches A and B are kept on, then only the circuit gets closed and lamp Y will glow. Construct a NOT gate using discrete components and verify its truth table. Construct the NOT gate using discrete components as shown in the circuit diagram on the general purpose PCB. Power on the circuit by applying 5 volt. When the input terminal of the circuit is grounded, it is equivalent to applying logic 0 and record the voltmeter reading and the status of LED. When the input of the circuit is connected to plus 5 volt, it is equivalent to applying logic 1 and record the voltmeter reading and the status of LED. Confirm the recorded values and to have a clear understanding of the logic levels, verify the truth table of transistor logic, NOT gate IC7404. Test the IC using digital IC tester to confirm its good working condition. Exchange IC if found defective. Construct the NOT gate test circuit shown in the circuit diagram on the general purpose IC test board pin board. Switch on the DC supply plus 5 volt to the wired circuit and check if the IC is getting excessively heated up. If the IC is getting heated up, switch off power supply. Measure voltage level at VCC and GND pins at the IC to confirm that supply is reaching the IC. Apply logic 0, low, ground 0 volt to the input of the inverter 1 of wired IC NOT circuit. Record the output voltage, corresponding logic level and status of LED in tabulation. Give logic 1, high or plus 5 volt at the input of the same inverter and record the outputs as done. Modify the wiring of the circuit to test the next NOT gate between pins 3 and 4. I hope after watching this video, you can practice on various logic gates and circuits by constructing an OR gate using switches, constructing an OR gate using IC7432, constructing AND gate using lamps and switches, constructing an AND gate using IC7408, and constructing a NOT gate. Thank you for watching. Have a good day.